Good morning, everyone. As Andrea said, my name is Jennifer Burt, and I'm a postdoc at JPL, where I work in the Exoplanet Exploration Program Office, and I normally focus on kind of precision RV mass measurements of exoplanets. And today I'll be trying to address, like I said, this daunting question of how we mitigate stellar variability that we see in RV data. So those different stellar phenomena that Heather and Annalise described during their talks all help produce the variability that's evident in this set of solar RVs. And Annalise just showed these taken by the HARPS North instrument. And you can see that even after we remove all of the RV shifts due to the solar system bodies, the sun is still moving around at the 5 meters per second level, which is 50 times larger than the RV signal of the Earth, which is shown in blue, down at about 10 centimeters per second. And that fact should terrify, at least a little bit, any planet hunter in the room, because as far as things go in the galaxy, our sun is actually considered to be pretty quiet. Now, with just the RV measurements, it's almost impossible to disentangle which bits of the star's motion are due to which type of variability, let alone to accurately characterize the different components so that we can model them out. So, how do you detect and measure stellar variability? So if we want to treat these different forms of activity as signals that we can model and remove from our data instead of just treating them like noise, then we need some way to detect and measure them either with our own RV data or some other auxiliary data set. Now, fortunately, the high resolution, high signal to noise spectra that are generally required for doing precision RV measurements also contain a plethora of additional information that we can use for exactly this purpose. And so I'm going to start by walking through some of the different activity indicators that you've heard mentioned during previous talks and that we use to try and better understand what the stars are doing. So possibly the best known activity indicator for RV surveys is the Mount Wilson S value, which is based upon the calcium-2 H and K lines. These are two very large absorption lines down in the blue part of the spectrum. These lines reflect the star's chromospheric and photospheric activity levels. And when a star is more active or has more spots on its surface, we expect to see the cores of these two lines show signs of emission. And so in the plot on the right side of the screen, you can see in the top panel the H line, and it's that big blue absorption feature. It looks like a big V, and that's for an inactive star. And then for an active star, you see the same line plotted in red, and you can see that at the very center of the line, we start to have this emission feature that peaks up. And the same thing is true for the K line shown in the bottom portion of the plot. And so the way that we measure the calcium index is by adding the flux in the H and K lines and then dividing it by the flux in two nearby continuum regions that we don't think should show variations due to stellar activity. So by measuring that index over time, we can look for signs of periodicity. And it turns out that when you look at the results of long-running S-index or S-value surveys, like the Mount Wilson survey, there are periodic signals everywhere, especially for sun-like stars. So this figure from Baliunas et al. 1995 shows the S values for just a handful of the stars that were tracked at Mount Wilson. And you can see periodic or at least quasi-periodic signals present in the majority of the stars presented here. Now, related to the calcium-2 H and K lines and the S index is the R'-HK index, and that uses those same two absorption lines, but it applies a correction that's based on the target star's effective temperature. And that allows for measurements to be compared across spectral types. Because when you're using just the S values, it's hard to compare the activity of a G star and a M star because they're going to have different base flux levels in those lines sometimes. The R'-HK also subtracts off the photospheric flux that falls into the S-index filters, which is not related to magnetic features rotating on and off the star, so it's a basal measurement. And while the R'-HK value is much better suited for activity studies, as it does not show the same dependency on stellar parameters like effective temperature that the S values do, it is also harder to determine because you need to provide some measurement or estimate of the star's photospheric flux, and that's a bit tricky. But it is possible, however, to convert an S value to the corresponding R'-HK value by estimating a conversion factor that you can see over here. So if you know what the H and K flux is, and you can try to subtract off some measurement of the photospheric flux, you can then correct or divide by the effective temperature to deal with this conversion across spectral types. Looking further into the red part of the spectrum is another well-established activity indicator, the H alpha absorption line. Similar to the approach used for the calcium-2 lines, this indicator is based on the ratio of the flux in the core of the H-alpha line to nearby continuum regions of the spectrum. H-alpha also tells you about the star's chromospheric activity levels because H-alpha photons are emitted in regions where magnetic field lines are influencing plages. And so this figure from Robertson et al. 2013 shows the H-alpha absorption for the star Gliese 270. And this is the star in states of high activity shown in red and low activity shown in blue. And so once again, you can see that the higher activity times correspond to filling in. The core of the line starts to fill in and be shallower than during low activity. Now, by extracting that indicator from the time series RV data, you can again look for evidence of sinusoidal variations that suggest the presence of spots or plages rotating on and off the star's face, and those are pretty clearly evident in this case of Gliese 270. H-alpha can be especially useful when you're trying to do characterization of cooler M-dwarf type stars, where the calcium H and K lines are often hard to measure because M-dwarfs don't emit a ton of flux in the blue part of the spectrum, and because they can often be fully in emission for those stars, so it's harder to detect time variability. Now, even further into the red are the three lines that make up the calcium infrared triplet. You can see them plotted across the top here. And these are considered by many to be one of the more promising activity indicators for the growing population of near-infrared precision RV spectrographs that are coming online. Following a similar approach to the previous lines, we're once again measuring the flux in each of the line cores and comparing it to nearby continuum or reference spectra. And you can see in the top figure, lines that are shown at observations of high activity in red and low activity in blue, and then kind of a median level shown in black. And these lines all show a clear anti-correlation with H-alpha, as you can see in the bottom plot, which suggests that they are also sensitive to variations induced by spots and plages on the surface of the star. Now, in addition to looking at specific absorption lines, we can also consider the shape of all absorption features in the spectrum, and Heather touched on this a bit earlier with the bisectors. True Doppler shifts should preserve the shape of the star's absorption lines and should not produce any line asymmetries or skews. But line shifts that are due to stellar variability often do change the shape of the line and will introduce some sort of skew in the line shape. And so the most common way to track the shape of spectral lines across numerous spectra is the line bisector, which traces the center of the spectrum's CCF as a function of depth below the continuum. And so again, you measure the kind of midpoint at each depth of your absorption feature or of your CCF, and you trace the shape of that. And if you see a curve to it, that means there's probably some stellar activity involved. The span of the bisector is the difference between the bisector position near the top of the line and the bottom of the line. It's measured in units of velocity, and it's usually designated as the BIS value. On the right side of the plot here, you can see the bisectors are extracted for two different phases of this potential planet's RV curve. And if you look at the first phase, you can see that all of the bisectors have the bottom of their lines pulled to the right of the midline that's shown by the dotted curve. And then if you look 180 degrees later, when the planet should be on the other side of the star, now suddenly all the bisectors have their bottom portions to the left of that dotted line. And that is concerning, because if we compare the RV measurements and the bisector spans that are measured at using the same spectra, and we see signs of a significant correlation, which we do here, those make a pretty convincing line, that should throw up a very big red flag that the signal is not due to the reflex motion of a planet, but rather the spectrum is probably being affected by some type of stellar variability that's skewing the line shapes, in addition to shifting them back and forth. Another activity indicator that's based on the whole spectrum and not just a single line is the Chromatic Index, which was introduced by Zeichmeister et al. In 2013. The Chromatic Index quantifies variations in RV semi-amplitude as a function of wavelength by measuring the K value, the semi-amplitude of a given signal in each of the individual orders of the shell. And then you fit a line to the resulting wavelength versus semi-amplitude data set, and the slope of that line is the CRX, or the Chromatic Index. Now, for a Keplerian signal, we would expect the RV semi-amplitude to be the same across all wavelengths, whereas shifts due to active regions like spots should exhibit larger RV shifts in the blue than they do in the red part of the spectrum, because the spots show less contrast at the longer wavelengths. Now, in this example, which uses Carminus data, there's a very pretty sinusoidal signal that shows up for this young star YZ Canis Minoris. But the Chromatic Index RV correlation demonstrates that the dominant effect in the RVs RV variations of YZ Canis Minoris is actually wavelength dependent, which is consistent with the hypothesis that these are caused by co-rotating features such as active regions and not by a planet. Okay, so that was kind of a quick whirlwind tour through some of the most commonly used activity indicators. So how do we actually mitigate the stellar activity? Now, fair warning for those of you who haven't already seen the spoiler in my pre-recorded talk, this is still a work in progress. There is not currently a single approach to measuring or mitigating stellar activity that can be applied to every star, nor is there a single approach that would be agreed upon by every exoplanet scientist. This is an area of very active research, and we're making good progress year after year, but it's still evolving. So take all of this with a grain of salt. Okay, now that we've covered that important caveat, let's go. So option one is kind of a cheat, if I'm honest. One of the easiest ways to mitigate stellar variability is to just not observe stars that are super active, because then you don't have to mitigate it. Now, there are a few different ways to do this if you're setting up a new survey. You can use a given star's Mount Wilson S value to predict its chromospheric activity even before you obtain RV datasets. So by combining a star's median S value with its B minus V color, which is a proxy for the temperature of the star, you can calculate the expected jitter following the steps that are outlined in Isaacson and Fisher in 2010. This is exactly what was done for the Lick Carnegie Exoplanet Survey that ran for almost 2 decades on the Keck high-res instrument. And in general, as can be seen from the blue histogram in this plot, they limited the survey to stars with expected jitters below about 5 meters per second. The right histogram shows the actual median internal uncertainty for each star included in the survey, and you can see that it ends up being pretty well matched to the blue histogram. And so this was a good selection criteria. But nowadays, when we're starting to look for planets that have semi-amplitudes at the 1 meter per second or even below level, no star is quiet at that point. Like no star is actually just sitting quietly and behaving itself at the 10 centimeter per second level. So this criteria is not necessarily going to save you. For stars where you have photometry in hand and you're deciding whether or not to pursue RV follow-up, you can use the FF prime method that was defined by Suzanne Augrain in 2012 to get an estimate of the star's RV jitter. So in this case, the most light curve for the star HD 189733 is shown in the top panel, and the RV curve that was predicted using that photometry is shown as the gray line in the bottom part of the plot. And then the actual RV measurements taken using the SOFI spectrograph are shown as the black points with error bars on them in the bottom part of the plot. And you can see that the predicted RV curve in gray is actually a pretty decent match to what was really observed by the black points. And so from the light curve alone, you can get a decent idea of what the RV variations will look like for a given star, and then decide if that star is well suited to the mass measurement you're trying to obtain. Another light curve to RV predictor is the star's flicker value, which was described by Fabienne Bastian in her 2014 paper. The figure here shows the light curves of 12 different Kepler stars, and then lists in the upper left corner their corresponding RV RMS measurements. The RV jitter seems to be most sensitive to higher frequency photometric variability, especially in the lower amplitude stars, so stars that look like they are quieter in terms of photometric motion. So the light curves, which are sorted by increasing RV RMS, show a general progression in their qualitative behavior from relatively low frequency variations to increasingly stochastic variability. And the latter stars, despite appearing non-variable by traditional senses, we don't see like obvious sine curves in them, actually possess a much more complex high frequency variability, which in turn produces the highest levels of RV jitter. Now, of course, the detailed behavior across figure 1 is not simply monotonic, because some stars have photometric variations with both low and high frequency content, but nevertheless, it seems like it's the higher frequency photometric variation that is a good indicator of what the stars might be doing in their radial velocities. Now, once you've decided which stars you do and don't want to observe, you then have to decide how to observe them. And good observing practices can also help to mitigate stellar variability, especially the shorter period signals. I think Heather, or maybe Heather and Annalise already talked about this a bit, but the first and easiest to address signals are the stellar oscillations. These often have periods in the 5 to 15 minute regime, and so you can make sure that your open shutter time on a given star covers at least that much clock time. And then you should be able to average these down. And so an example of this is seen in the data for Alpha Cen B. This was shown by Xavier Dumusc in actually a previous Sagan workshop. And you can see that as long as you observe the star for at least about 5 minutes, the amount of the amplitude of the RV RMS comes down pretty rapidly. Now, the exact averaging time necessary varies as a function of effective temperature and luminosity and surface gravity. So you can't just assume that 5 minutes is the right answer for every star. But you can check out this paper that came out last year from Bill Chaplin and Heather Segla and others. And they've actually got a nifty little Python script that will tell you, based on the star's parameters, how long you should be making sure to observe for. And an example for some of the stars included in their work is shown in this table. Observing strategies can also help to mitigate the effects of granulation, which, as we heard earlier, occurs on timescales from hours to days. The same concept used to average out the pulsation modes can also be applied here, but in this case, you're trying to average out signals that last most of the night. Now, fortunately, there's no need to just sit on a single star for the whole evening, which would kind of ruin any attempt at carrying out an RV survey of more than one star. Instead, you can catch the star once as it rises, and once when it's overhead, and once when it's about to set. And by sampling the star multiple times per night, you can move from the top black line in these figures, which is the RMS you get from observing once per night, to the black dashed lines in the figures, which is what you get from observing twice per night with 5 hours between your observations, to finally the pink lines, which is what you get from observing 3 times per night with 2 to 3 hours between those observations. So we can start to bend down at least a little bit the granulation. And then if you know something about the planet that you're trying to observe, you can also design an observing strategy that's very short and intensive to try and recover the period. So in the case of Proxima Cen b, there was multiple years of data that were taken before 2016. That's the periodogram in the top. And you can see that the suggestion of this 11.2 day signal that's rising up and cresting that kind of second dotted line in terms of significance. But despite the signal being relatively strong, the analysis of the pre-2016 data produced slightly different periods and masses depending on the noise assumptions and which subsets of the data you used. So what the team did in order to confirm the planet was undertake an intensive observing campaign in 2016 where they observed the star almost every night between January 19th and March 31st. And they took 1 spectrum per night, and that is what provided a definitive detection. So this 2016 data is shown in the bottom left periodogram, and then the combined data is shown on the right. Now, at an amplitude of 1.4 meters per second, Proxima Cen b isn't especially small in terms of RV signals, nor was the pre-2016 data lacking in terms of number of observations. There was a fair amount of data there. But it appears that the uneven and sparse sampling of the data in the earlier years meant that it was hard to recover and distinguish the planet from the star's activity. And so by doing this intensive observation campaign, it became much easier to pull those apart. And then even in cases where your observing strategy can't average out or mitigate stellar variability, you can still make sure that the data collected has all of the right characteristics to help you try and model the variability after the fact. So in particular, that means that you want to aim for high resolution and high signal to noise observations. These results from Davis et al. 2017 demonstrate how different combinations of resolution and signal to noise impact the number of principal components that can be recovered from different simulated data sets that have different spot and faculae coverage fractions. Now, in general, the more principal components that you can recover, the greater the information content. And so in an ideal world, you want to be up in the upper right-hand corner of these plots. But unfortunately, it turns out that a resolution of 300K is not readily available on most currently operating RV instruments. And so most of us are actually operating somewhere in the mid to lower left region of these plots. But these kinds of very high signal to noise and very high resolution observations might become necessary if we truly want to understand the nuances of how stellar variability impacts the shapes of lines and RV shifts going forward. Okay, so let's say you've collected the RV observations for your star of interest and you've done your best to follow all of these observing best practices. It's highly likely that there's still some level of activity and variability left in the star. So how do you deal with that? Well, one of the more straightforward approaches is to model the signals caused by stellar variability as additional Keplerians, additional sine curves in your data. This approach is called prewhitening, and it consists of looking at a periodogram of the RV data and identifying the strongest peak. And in this case, you can see it identified with the planet label. The strongest peak in the RVs is indeed the planet orbiting this star. So you fit out that signal, you get the nice sine curve in the upper left panel of the left side plot. And then you make a new periodogram of the residuals and you look for additional strong periods. And in this case, when you look at the residuals periodogram, which is shown on the bottom right, you see 3 more peaks that I've identified with purple lines, and those are all due to the rotation period of the star and the harmonics of that rotation period, the half and third rotation periods. And it's only after you identify and model out each of those periods as well as additional sine curves that you get to a point where there's no more significant power left in the periodogram. That's the dotted blue line at the bottom of that periodogram. And you can say, okay, we think we've addressed all of the main signals. For cases where you have activity indicators along with velocities, we can start to get a little more creative. One traditional approach is to look at a time series of the indicators, in this case, the calcium H and K lines of the sun, and identify any prominent periods that appear in the calcium data, which are likely due to activity signals. Once you identify variability and the period of it in the calcium data, you can then use that derived period to fit a Keplerian in your actual RV data, where you fix the period, but let things like the amplitude and the other orbital parameters vary a little bit. That model is then subtracted from the RV data, and you have cleaned the RV data of that activity signal, which will hopefully make any real RV signals more apparent. A related approach is to compare the calcium index to the RV signal, or to the RV measurements. And if a strong correlation is evident, then you perform a linear fit between them. And each RV point can then be corrected based upon its corresponding calcium value, removing the variability-based trend. So in both these cases, the focus is on using information from the activity indicators that you've extracted to then better treat what's happening in your RV data. Though, as Annalise mentioned, there are a number of issues that can crop up when using this kind of treatment, so it's generally not suggested anymore. A third approach, which works best for exceedingly short period planets, is the floating chunk method. So in this case, observations taken over the course of the night on a, taken over the course of the night on a single night sweep out a non-trivial portion of the planet's phase curve. And so the velocity segment that you get on a given night will be offset from the planet's true velocity curve by some amount, either up or down in RVs, and that's due to the presence of stellar variability or additional long period signals. But by including an additional nightly offset term in your RV fit for each night of data, you can line up all of those little purple segments and reconstruct the red planet phase curve in this figure. A nice example of this is seen here for the results of the ultra short period K2131b. The circles are PFS data and the triangles are Harpson North, and each color represents the data from a single night of observing. And you can see how a single color and shape, like the red triangles, for example, span a significant portion of the orbital phase. They sweep out kind of the lower quadrature portion of this star. And so by adding an additional offset term, we are able to bring all of these points into line and reconstruct the planet's phase curve. One of the most prolific planet detection methodologies in the past decade is the moving average approach, or used in things like the Agatha analysis package, which applies a model that's built around the understanding that RV data contains a variety of signals. So these models include Keplerian signals to account for the planets, white noise to account for photon statistics, red or correlated noise to account for stellar variability, and then the option to fit linear correlations between the RV data and the available spectroscopic indices. And the result, as you can see in the Bisector periodogram shown here, is this comprehensive analysis that compares 3 different noise models, which are the things in the top 3 columns, and then working down, and then applies those to the combined RV data set in the top row, the individual instruments data sets in the next 2 rows, the activity indicators, the window functions, the signal to noise of the data, etc. So it does this kind of deep dive into your data. If we zoom in on just the RV data and compare it in the white noise and moving average cases, you can see in the white noise panel, there's a strong but somewhat scruffy peak at roughly 30 days shown by the gold line. And then there's another strong but kind of scruffy peak at roughly half that period, which we think is the kind of p/2 harmonic. This is reminiscent of what we would expect if the 30-day signal was caused by stellar activity. And this is all in addition to the much stronger and narrower peak at 12 days that we suspect to be a planet. Now, if we look at the S-index data from one of the telescopes involved in this analysis, the APF, you can see that there's a corresponding peak at that gold line, that 30-day period. And so that confirms our suspicion that that's probably due to activity. The benefits of the moving average model are pretty apparent if you look in the top right periodogram. because you can see that when you apply a moving average model, that basically identifies and removes both the 30-day rotation activity signal and the harmonic of it, but it leaves the 12-day period that we think is due to a planet. And so this is actually a new system that we're in the process of writing up right now. So this approach worked really well for us. In order to try and avoid the impacts of stellar variability, we can also try and measure RVs using only those lines that are not sensitive to activity, which is what Xavier Demusque did in 2018. So to investigate whether this is possible, he took an intensive set of HARPS data for the star Alpha Cen b during a time span where we know that the star's RV signal was driven by stellar activity. He then measured the RV variations of individual lines, 6,000 individual lines in the spectrum, and compared the motion of each line to the overall motion of the entire stellar spectrum. So any individual lines that have RV motions that are correlated with the overall RV motion, like the two examples in the top panel, are being driven by activity, whereas any lines that don't show correlated motion, like the bottom panel, are not being driven by stellar activity. And those bottom panel ones are what we'd like to use for measuring the star's motion. The scatter plot on the left here shows the correlation coefficients measured for the 6,000 lines that he investigated. And if we plot the RVs derived from the whole data set, we get the black time series shown at the top of the right side panel, and that has an RV RMS of about 2 meters per second. If we plot just the lines that showed strong correlations, the red part of the scatter plot, we get the middle panel, and that has an RV RMS of almost 4 meters per second and shows a stronger correlation or a stronger motion that is tied to activity. But if we take just the lines that are from the center part of that scatter plot, the blue lines that don't show much correlation, then we get a much calmer RV time series, and the RV RMS drops down to about 1.2 meters per second. So there's still correlation, there's still activity. These stars are not perfectly independent of what the star's variability is doing, but this is a promising approach. And then finally, what is probably the most popular approach to mitigating stellar variability in RV data right now, the use of Gaussian processes. Now, I'm not going to delve too deeply into the specifics here, both because I am not an expert on Gaussian processes, but more so because Vinesh has already done a whole pre-recorded talk focused solely on this topic and also talked about them in some detail in yesterday's panel, but I'll try to cover some of the basics. So Gaussian processes work under the premise that variability signals are correlated and are often quasi-periodic with a handful of key parameters that define their behavior, which are called hyperparameters. Now, generally these hyperparameters represent things like the star's rotation period, which is the recurrence timescale hyperparameter, and the lifetime of active regions, or the evolutionary timescale hyperparameter, among others. Users specify priors for the hyperparameters that are generally gleaned from other data sources like light curves or spectroscopic indices, and the GP then attempts to model what the star is doing alongside what the planet is doing, which can allow for reasonable RV fits to come out of data that is very impacted by stellar variability. Such as the example seen here. So these are RVs for the young, relatively active star Kepler-78. And you can see here that the RVs from high res in HARPS North, shown in blue and red respectively, show variations at the plus or minus 20 meter per second level. The planet that they detected in Kepler had an expected RV signal of about 2 meters per second. So this was a rather daunting RV data set to try and extract a tiny signal out of. But by training the Gaussian process on the Kepler photometry, you can see that the models shown in blue and red lines actually do a pretty good job of passing through the majority of the data points. So we think we are reconstructing what the star is doing and what the star's overall motion is pretty well. And so the result is that you get this very nice looking sine curve where the data points are shown in their respective colors. And then the gray dotted line is the model for the planet that results from the Gaussian process fit. And the black data points are the binned RVs. So if you take all those color points and bin them down in phase space. And so we get a very nice result despite this very high level of stellar activity. And just to drive this home, if you plot the amplitude of that planetary signal, the plus or minus 2 meters per second, on top of the original RV time series, it covers a y-axis range that's equivalent to the height of this green bar I've just put up. So this is a very tiny signal that is imposed on top of a very active star doing things. So it's a little bit crazy that we can pull this out. But even in the case of copious high signal to noise data to train the GP on, you still need to be careful. And so recent work by Molly Kosharik that Annalise mentioned earlier looked at 70 years of solar irradiance models from the Empirical Irradiance Reconstruction Project, or EMPIRE. She used a GP analysis on each individual year of the solar photometry, and the posteriors of the GP hyperparameters are shown here, with the recurrence timescale, the one that represents the stars or the sun's rotation period, in the third plot. And so the gray bar represents the correct value, the star's rotation period, and the black outlines show the distribution from a straightforward GP fit. And if you look closely, you can see that for the most part, the thick part of the black shapes, the black violin plots, don't line up with the gray bar. And so that means that the GP is getting the answer wrong. The GP thinks the rotation period of the sun is different than the correct answer. But if you add an additional requirement that the evolutionary timescale must be larger than the recurrence timescale, that is, that the same spots are going around the sun at least a couple of times, so you see them come back around, then you get the results in blue. And where the thick part of the blue shapes is almost always contained within that gray bar, that is the correct answer. And that requirement is well justified, both based on our observations of the sun and observations based on 4 years of Kepler data for many hundreds or thousands of sun-like stars. So I find that this example, where it's possible to get the rotation period wrong, even though you have years and years of very high quality solar data to throw a GP at, is a good reminder that we need to really try and apply and incorporate all of our knowledge about a given data set into the analysis, instead of just trusting an exciting new methodology to handle the nuances for us. Because if you incorporate all of your knowledge, it is possible to get the right answer. Okay, so as I said at the beginning, this is all still a work in progress, and I think that trying to overcome the difficulties presented by stellar variability will be the biggest challenge of RV science in the 2020s. But we're learning now to focus on much more detailed characterizations of the stars themselves, and trying to understand not only what the radial velocity what their radial motion looks like, but also how those stars breathe and shift and evolve on timescales from minutes to months. And so as long as we stay focused on that and keep pushing our understanding forward using both stellar and solar data, then I think we'll have a better understanding of how those different physical phenomena that Heather and Annalise discussed really impact the shapes and positions of the absorption lines, and how they can be modeled and mitigated, removed from the RV data. And so with that, I will say thank you so much for your attention and ask for any questions.
Yeah, thanks a lot. There have been a lot of questions, but we don't have much time. So one question was regarding how these relations that we know from the sun and G-type stars may scale to K and M dwarfs, and how things that we measure in, for instance, the S-index that are more related to the chromosphere relate to the photospheric lines that we use for the RV measurements.
Yeah, so scaling to lower mass stars. So in general, I think what we've looked at so far says that K stars tend to be a little bit less active than G stars. And so those are becoming a bit of a sweet spot, because in many ways they are still sun-like in terms of their SEDs and the amount of energy they give off. And so those are an attractive set of targets right now. I think a lot of surveys are focusing on those a bit more. For the M stars, things do start to change quite a bit. The amount of energy they give off and the type of energy is quite different. The spots are often a bit more apparent when looking, and so it can be easier to see kind of the rotational modulation of the stars. But things like the calcium lines that are the traditional activity indicator for sun-like stars, like I said, are often very hard to measure for M dwarfs. And so I think there's effort starting now, and it has been going for a while, to try and bootstrap back to the S-index by either measuring the calcium infrared triplet or measuring H-alpha, and trying to do that for stars where you have a spectrograph that has a broad enough bandpass to get multiple activity indicators and see how they compare.